So why not? A little bit of an animation has never killed anyone. Good morning. So this is the start of the recording. I already had a couple of sentences before, but they were irrelevant. The ones following those, however, are probably going to be relevant, or so I hope. So it's not skipping the appropriate slides. Oh, that's problematic. I'll have to do this by hand. Oh no. Always some technical hurdle. So today on Primer, we're going to talk about randomly spiking neural networks. Let me give you an outlook for the day today. So we're going to have a greetings and outlook. Greetings, hello, and outlook. The outlook is our story arc. As I mentioned last lecture, I decided to have slight modifications in the order that I had presented in the first lecture. And particularly, the new story arc goes a little bit like this. So we focused on the biophysical models of the single neurons, like the Hodgkin-Huxley, on lecture number 1. Understanding all of the details about gating equations and so forth and so on. Then we went into simplified models of spiking, and you've done a project, hopefully, where you learned more about the adaptive exponential integrating fire neurons. And I'm going to review a little bit of that today still. Then today we're going to look into random spiking neural networks and how parameters such as synaptic inputs affect them. So we're going to also talk about synapses today and focus on the leaky, integrate, and fire neurons. More about that in a second. In next lecture, once we already have an understanding of how spiking networks not process information, but what kind of spontaneous activity can they engage in, we will look more closely into meaningful information processing through encoding and decoding in neural networks. Talking also a little bit about sensory motor loops and generation of behavior in a large spectrum. We're also going to then look more into these structural functional relationships that I've mentioned before, what kinds of networks lead to what kinds of behavior. And definitely we're going to be focusing on simplified networks already at that level. We're going to be looking more into high-level neuronal models, such as the ones that are used in artificial intelligence nowadays, the rectified linear unit, the sigmoidal units, non-spiking networks ultimately. Between today and next day, not only will have this project, but you will also have a tiny little homework assignment, which is about constructing networks via graph representations of connectivity matrices. You will have sufficient information from that little homework. So this is then in lecture 4, we're going to be focusing on encoding and decoding. So we're going to be talking about receptive fields and about hierarchies of processing. Hopefully we will get the chance to also cover feed-forward neural networks all the way up until convolutional neural networks and deep learning. You notice that day 4 is fairly packed. Might be that we will need to send a little bit of that to the 5th day. And in the 5th day, we're going to be looking into unsupervised learning and plasticity of simplified networks, of simplified recurrent neural networks, and the kinds of things that they can do, such as memory, particularly, we'll be focusing on. So this is then the grand story arc. Today will have a little review of 2D dynamics. I could imagine that not all of the components came together. This is a build-up process. So I just wanted to come back to the two-dimensional Fitzhugh-Nagumo that I could not present last time because I had a technical hurdle with Mathematica, but I got it to work. So I wanted to present that to you. We already have an idea of two-dimensional phase spaces, but I wanted to get back to that, also give you opportunities to ask questions that might not have become, that might have popped up in the meantime. Then from 2D neuronal dynamics, we're going to skip on to one-dimensional dynamics and leaky, integrate, and fire, so thresholded models. The adaptive exponential is also a threshold model, but it's two-dimensional, but it's a threshold model. We are going to slash one more dimension, losing some generality, but gaining a lot of simplicity and explanatory power along the way. So we're then going to be looking into networks of leaky, integrate, and fire neurons. And to hook up networks together, we will need a couple of things. One is an understanding of what synapses look like, and you will find it fairly simple in face of what you have already learned, what synapses mostly do. I will, however, also go a little bit deeper in detail of more sophisticated synaptic models, such as Markov models, so that you at least know that they exist. They might become relevant in your nanobiological future because they take the formulation that is more structural in nature, that it's a level we don't focus into in this course, but it's very interesting to think about where, little mechanisms happen. We've been looking a lot into ordinary differential equations as representing the biological phenomena, but we can have finer grained, more detailed in synaptic models. I'm going to then present you to the Markov models. We're then going to have an intermission, and I'm going to swiftly explain the two other necessary components for the projects that you're going to be going through. Today is a day that is going to be, the project is sizable, but also, I guess, very manageable, I hope. And so I reserve the rest of the lecture after we talk about random input and random connectivity in random spiking neural networks for your project with questions and answers. I've noticed that there's scarcely time to get into the project when you are taking, when you were taking the lectures, like the previous lectures. That give the project, get very few questions through the scored, almost none. And from my experience in computational science, this has to do with the fact that people are still going into the project as lecture finishes. You barely had the time to even get your bearings within the project. So I'm going to try to give a little bit more time. I think it's a very fun project to do because you're really going to see some, networking, spiking activity. And this also prepares you for the course upcoming, systems in neurobiology, in which you're going to be talking about spike rasters and histograms and spiking activity, spontaneous activity, quiescence, and synaptic transmission and so forth. So I think it's a project that is very information rich, and I'm looking forward to your feedback from it. And then I wanted to wrap the lecture today with a joint discussion. You probably will not have finished project by the end of the lecture today, but from 12 to 12:30, I wanted us to gather here again in Zoom and have a look into what doubts may have occurred, and actually also philosophical doubts I wanted to discuss with you, because it's very natural that you have many questions surrounding your mind. Why, like all these random things, what do they mean? So the emphasis today is on random spiking neural networks, not pattern, not networks that are processing stimulus, but more networks that, given that they are cobbled up together randomly, what do they do? So the fun thing about this randomicity is that you can think about randomicity as the space of everything that is possible, given that you have neurons and they're connected. It is the superset of the more constrained subset of functional dynamics, the ones in which you're actually processing stimulus to respond to things in the world. But these give us very sharp constraints over what kinds of behaviors we might expect from networks that are actually processing stimulus. So even though they're random, they include as a subset of them all of the functional neural networks that we're going to be discussing afterwards. And they provide then a perfect context for you to go into what the networks then of spiking neurons and then further on simplified networks can in principle do. Spiking will happen in both networks, either they're functional or not. And so if you understand what are the causes of spiking and what are the conditions that bring it about, this will give you, I hope, a vision of a background vision of what spiking networks can in fact do even in the brain. And without further ado, I hope that I noticed that my skipping slides are not working, so I might have to go back and forth here. But the next slide, I hope, is a two-dimensional a two-dimensional ODE. So model. Actually, this is a Fitzhugner, not a Fitzhugner-Gummel type. This is a sodium potassium type with a cubic. Two equations. One that gives you the change over time of V, which is the cubic equation here. And another one that is an exponential refractory variable that has this nucline here, the dashed nucline. The dashed nucline. The vector field is represented by the tiny little arrows given the two equations. The equations are not even shown, right? They're not even shown. And in fact, in the book from where I get this, they're also not shown. So this discombobulates some people. The reason is that it doesn't really matter. I mean, what matters is what the nuclines look like, in fact, for you to understand qualitatively what kind of dynamics they have. So let me just make this caveat here. We're interested in the phase space and the nuclines. So if you have questions about nuclines, again, I'm going to get them. I get to them in a short second. Ultimately, since you have two equations, V dot and W dot, which are some function of x, y, or a function of v and w, and another function of v and w for w. The nuclines are the places where the dynamics on one dimension equal 0. I can quickly remind you of this fact via sharing this screen here. So if you have two equations now, so f dot, which is v dot, which is some function of v and w, a refractory variable representing, say, potassium, and v, a variable representing the dynamics of sodium, for instance, and another w dot here that is another function of v and w. We can ask in the grand phase space of things of v and w, where are the places that the flow changes direction in one dimension exclusively? If you watched the 2D little tutorial we had before, this should have become blatantly clear, but I'm going to repeat it nevertheless. So here, if you have a v dot function, and in this case we make it a little cubic, our v dot is, let's say, red, and then we have a w dot that is something like this. These are the places. This is the nucline for w dot equals 0, and this is the nucline for the w dot for the v dot equals 0. So dynamics on the left and on the right side of the red line are going to change the direction of the v. So say, for instance, there's two possibilities, of course, left, or they can either go left in the bottom of the curve and right on the bottom of the curve, or right in the bottom of the curve and left above the curve. So in this case here, we can imagine that whatever is below the curve is to the right, and whatever is below above the curve is to the left. And here, in any point in this line, we have no horizontal component. So horizontal component is 0, hence the v nucline. How do you decide the direction? That's a good question. So did you, Sarah, did you actually watch the 2D tutorial on no clients that was online? I'm curious because this was answered there. You didn't fully understand. So ultimately what you get is actually an equation. So what you will be solving then is the inequality, right? So to find out which direction you actually have, you have no other solution but to apply here, for instance, an inequality in this equation. And this inequality then gives you effectively what happens when, you know, where is v smaller than 0. Watch it again. With this piece of information, it should become clear. So in principle, you solve this inequality and you will find out what is the domain of the phase space that actually has a certain directionality for you. Here we ask, so v dot larger than 0, then you can find a relationship between v and w such that v is like larger or smaller than some function of w. And through this relationship, you can determine which side of the curve is positive or equal. Well, you ask the question, so you hypothesize. So the question here by Sarah is, so you induce the inequality yourself. Yeah, you actually ask. So if v dot equals 0 on the curve, v dot is larger than 0 on what side of the curve? So that's a question that you ask to the equation. So you effectively induce the inequality yourself. You ask the question. Okay, so two-dimensional dynamics, just in a glimpse. This is the Fitzhugh-Nagumo model, also two-dimensional model, and this is continuous, has no threshold. It's not like the adaptive exponential integrating phi that we had before, and I'm going to create the distinction now between one and the other. So the equations that define them are these two. We have we have a cubic on V. So here, I presume that if I zoom in, you can actually see these equations I'm talking about. Here you have V dot equals V minus V cubed plus V plus a refractory variable. So when the refractory variable is positive, we actually have a tendency to have a positive change in V. So the larger the refractory amount, the larger the potassium, the more likely it is that you're going to be raising your membrane potential. You also have the I current applied here in the bottom. And you have a linear refractory variable, W dot. If you want to learn more about how this model comes to be, Scholarpedia, Fitzhugh-Nagumo, fantastic article, written by the model developers themselves. I think Fitzhugh actually wrote the model. And so this is a little bit mathematical code, very neat. So this is a demonstrator that shows for any initial state in this phase space here, what would be the trajectory. And you notice that we have a global single attractor in the place where the two no clients are intersecting, because that's the place where V dot equals 0 and W dot equals 0. And it's attracting the, because of the directions of the flow. You can also compute the Jacobian at the intersection between the two no clients. If you remember a little bit of stability analysis, we're going to get to that in dynamical systems. But right now, the idea is that you can compute the derivatives with respect to the to each of the variables here and decide whether this is a stable or an unstable fixed point, an attractor or settlement and so forth. No, I'm not going to get into that. I mean, I think that it's sufficient that you see that there is a field, flow field, that is guiding the trajectories from any starting point in the phase space. So these are all possible trajectories, and they're in this moment going to the global attractor. If I raise input current, if I raise the input current, the orange curve will rise a bit. Actually, before I go there, you notice that for certain situations in the phase space, I actually produce a fast transient that goes up a little spike, whereas for points that are fairly nearby, I produce only some sort of subthreshold oscillation and nothing else, right? So this is sensitivity to this initial condition, like at least in the case of the transient. This would be a phasic neuron, neuron that produces a single spike and it becomes quiescent. It doesn't produce spikes spontaneously or regularly like a tonic neuron. If you raise the input current, you will notice that the attractor no longer attracts at one point. So here, very close to this, to minus 0.5, I have the transition between a neuron that only spiked once, or maybe even not at all, to a tonically spiking neuron. Okay, so, and you see that we have the two curves, the V and the W, and both are plotted in the time series. And when you look at these spikes, you're like, well, these are fairly fat spikes, aren't they? I mean, like, you know, really very sizably chubby spikes. So this is one of the problems with models like the Fitz-Nagumo, because it has only two equations determining the dynamics. It doesn't have a really fast dynamics of the spike, which combination of sodium and kicking in of potassium channels will have, the inactivation of sodium and potassium channels will have. So it rises fast, that's good, but it falls slowly. There are spikes in the nervous system that are like that, but most spikes are much thinner, and the spikes that people were interested in when they were doing these models were also much thinner, maybe 1 millisecond, maybe half a millisecond long. And that's one of the reasons why people adopt the adaptive exponential integrate and fire neuron by setting a threshold at voltage someplace. You know, here we have arbitrary units, but one could set a threshold here, say, in a vertical line where, say, V equals 1. You set a vertical line for V equals 1, and for W's ranging over the whole thing here. And then you can impose a reset after the spike without loss of generality. You don't learn so much about the thickness of the spike, since you basically squeeze it to infinitesimal, but you do gain the ability of having more believable overall spiking dynamics. So it rises quickly, and you can then play with these variables to then obtain all the different kinds of spiking as we saw before. So this, as you saw before in the Zhikevich plots, where you have the multiple kinds of spikes and the adaptive exponential integrating fire neurons as well. So chat window. There are no more questions here. I'm going to move forward. Hence, we have learned that spikes are limit cycles or fast transients in the case of a single spike and nothing more. We learned that the trajectories exist for the whole phase space. We learned that attractors govern the appearance of spikes. And we haven't learned much in detail about the bifurcations themselves. So here, our panel D tells us what's the bifurcation scenario as a function of I current on the membrane potential of cell. And so ultimately it's a projection of a spike. I'm not going to go into that in detail. Just wanted to let you know that basically what you have here in this first thick line is a slow rising of the resting membrane potential until a moment in which you have the coexisting for high currents, you have the onset of spiking, but it could also for the same current be quiescent. So the center line is the resting potential that is simply changing position as you raise current, right? Imagine that you're rising the cubic curve a little bit, and like I just showed you, for some values you spike, for some values you do not spike. So basically here you're looking into bistability of these two scenarios. You can simultaneously have a cell that goes to a resting state and a cell that is tonically spiking in the same cell, right? For the same current applied. Depending on which is the initial state, you might have a resting cell or a spiking cell. This is what the panel D is showing. Now, we're not going to go into detail of bifurcation analysis. This is for dynamical systems later, but gives you a sense that we can inspect what would be the criteria for producing these spikes. But 2D is a lot of dimensions. In fact, we can do a lot of things with many less dimensions. And what we generally do is having a one-dimensional model by trying to restitute just the core part of of interesting dynamics. So here, like, let's go back to the one-dimensional state space quickly. And here, let's imagine that we can write a single function of a single state variable that would give us spiking. Can we do that? It's actually a hypothetical question. So can we write some function v v dot equals some function of, say, v and a parameter I and other parameters, but some function that produces something that looks like spiking? When I introduced the one-dimensional dynamics, the first function that I've used was just a line, and that line looked like this. And we found out, okay, so this is where that function is 0, and for this, in this particular case, we have an attraction over here. But that won't do because for spiking, because obviously, if you start at the high voltage, you converge into this attractor state. If you start with a low voltage, you converge into an attractor state. But there's no spiking. I mean, no matter how much current you put in. So if you now add some current, and this function is simply a line, so say a v dot equals minus v plus an I or something, and then you raise that curve by I here, your resting state attractor rises, increases a value. Say, it's going to go a little bit more, say this new attractor is going to be here, so new states are going to converge into this new attractor. But it will do this indefinitely, no matter how much current you input. It would only simply change the position of the resting state. So this will not do. Next thing we could try is we could maybe try some sort of quadratic function. And a quadratic function is nice because it will then, we can design a function that has a resting state, and that resting state looks locally equal to the line we had before. So it's attracting states like here, and it is also attracting these states. But if you raise the current for a certain amount, that state disappears, and you will have fast voltage rises. So this would be an interesting possibility, in which, you know, if you start with voltages that are high, so that is, if you give a current bump onto your function, then let's plot here the position of these two attractors, 1 and 2. For most states starting around 1 and 2, we would see something along these lines. So they're repelling from 2 and attracting from 1. And from states larger than 2, we would be having an infinite rise. So like it's quadratically rising over time. So any other point over here is going to rise quickly. Boom, boom, boom. So that is also not due. I mean, because it might even look like a spike rising, but it never will finish rising. So a quadratic curve can also not serve the purpose of representing spiking with one dimension. I guess that most of you already are thinking along the direction that I'm thinking, but you'd say, like, why don't you say it already? But I still want to walk you through these one-dimensional cubic or variations of the potential functions we might use for exercise. If you now have a third function, the quadratic won't do, but a cubic, I saw a cubic before, and a cubic looked promising. A cubic would have 3 equilibrium states, 2 stable equilibria, and 1 unstable equilibria, so that the starting conditions close to 1 would converge into the attracting state. The starting conditions close to 2, if they are on the left of 2, they would go to 1, and if they are on the top of 2, they would go to 3. So that's kind of nice. And you actually have another state that is a little bit more depolarized. So you have the coexistence of stable states, and you have something that would rise indefinitely, or in this case, actually, oh, wait a second. So did I, so rise, fall indefinitely. Okay, so fall indefinitely. So you have 2 stable states, still no good, not spiking. This is the challenge. Can you think about a function that will produce a spiking that, you know, after a sharp rise, say here you have a fast rise, but then you get slower and slower. Can you think about a function whose temporal domain actually does this over time? So we wanted to rise for certain values. For certain other values, we actually wanted to tend to the resting membrane potential. But for most, for elevated input currents, we would like to see a spike and back. Now, this would require, in a one-dimensional dynamical system, that there would be a way to do the following. You would have to depart from an elevated value for the voltage all the way very fast to a low value. But to have this kind of dynamics, you have to have negative voltage dependencies. You have to have your V dot being negative so that you can take this direction here. Problem is, in one dimension, you're constrained to do one thing at a time. So if you have a V dot that is negative over here, so like some curve that from here to here, say, is negative, delete this guy. So, some curve that is negative from here to here, it cannot rise. So in order for it to rise quickly, we would need some sort of curve that, some sort of function that does maybe something like this. So this is the conflict here. We need a function that rises quickly to a steady state to the right, but falls also quickly to the other direction. You cannot do this in one dimension. What you can do is you can imagine that you have the pink function by establishing a threshold somewhere else. Here, for example, in yellow. Let's get a better yellow maybe. A threshold function such that when our state that is obeying now the green curve is rummaging, so forget now the underlying pink curve. Let me actually delete this guy. So this guy doesn't exist anymore. We have simply a curve that creates a fast rise of the membrane potential. And we impose then a threshold such that when the state that is rising via that equation touches a certain threshold, or maybe the threshold is here, we, by hand, take the state and put it in some sort of resting position. You could put it here. In which case, it would actually go again, right? It would rise and knock on the threshold, and we would return to resetting state. If our green curve, however, say our green curve continues on the negative side here, if your resetting condition is in this domain, we would actually have a decreasing voltage, like infinitely, all the way to minus infinity. So this is then the challenge. You have to create a function that is well behaved, will have some sort of resting states, and will also have a threshold so that you can produce spikes and return to a reset. It's a lot of words from me, and I apologize, but I wanted to give you an idea from the one-dimensional state space. What are the challenges involved in creating an integrate and fire neuron first? So you can use a bunch of different functions, but each of them will actually have a certain requirement that has to be met for that integrate and fire neuron to exist. The first integrate and fire neuron was actually developed by a guy called Leaky. If you read this in 1907, he didn't derive all of these equations. He just thought to himself, like, oh, you see what I see? I've injected a bit of current, I produce a spike, and then it stops. So maybe what it's doing is actually adding the current that has been injected priorly, which is the main intuition we have. But now we also understand, like, how to parameterize these kinds of neurons to produce these different kinds of behaviors. So simplicity, more or less, right? It's one-dimensional. It's not completely trivial, but one can think about it in the context of the circuit and see what kinds of functions would give us the behavior that seems reasonable at this stage. So you now know that the current going through a circuit is the sum of the resistive and the capacitive currents. You then have this differential equation here now in U instead of V. This is from Spiking Neuron Models, Wolfram Gerstner's book. And nice thing about this dynamics, this is, you still see it's not a spiking dynamic. but it is a membrane potential passive dynamic that adds current and then decays back to resting state. Lovely thing about this is that it even has an analytical solution. If you inject current I0 at a certain early point, it will have a little bit of a decay as a function of the input resistance and the time between this input and the future. So basically, give it a bump with the current, which then slowly falls off. So this is the dynamics of a passive membrane exclusively, without much care for all of the units, but gives you the same idea. So just to complement this picture, what I am talking about here is the circuit where you have the capacitor and the resistor, and you're applying certain current at time t, and so if this current is so the R and C, if this current is applied as a perturbation, like fast, and say you add a step of current like this, then your membrane potential is going to rise and then fall via the capacitive component. So, okay, so this is what the passive membrane does, and it was the beginning of Hodgkin-Huxley project. But this is not spiking. Well, if you give a larger current, it will produce a larger voltage diffraction, but it will still fall. But the trick is, we don't care. We don't care it doesn't spike. We just say, well, when it's big enough, it is actually spiking. And then it is actually returning to a resetting condition. So now what I'm showing here is the dynamics in red of the integrate and fire that has received a sizable current. And this is a leaky integrate and fire because the membrane is passive, and so after you inject current, it leaks. And after it crosses a certain yellow threshold, it produces a spike. We just say this is where the spike happens. We can relate this to more complex models and talk about fast dynamics, but we're not gonna. We're just gonna say threshold, spike, falls, continues, imposing it by hand, and so returning to the resting condition, just in the same way as we had our linear model. In a one-dimensional system. So it returns to this resting state, but when I apply a high enough current and I shift the dynamics here, I also impose a threshold that when the state touches it, I just basically teleport the state to a resting value. So this is the dynamics then of the one-dimensional differential equation representing the leaky integrate and fire neuron. So this is the LIF, the leaky integrate and fire neuron. So in terms of a circuit, we have a threshold introduced. Now this funny V here is actually a theta, a cursive theta, and it's a resistor, right? It's like it basically, when it has a sufficient voltage between the two, it actually produces a pulse, transistor, I want to say. But a threshold, really. So membrane potential rises substantially. We impose a value from which we just say produce an event and cut that input. once you have a model that acts as I was explaining, you have a lot of really neat abilities. I mean, it's so simple that it's very amenable to analysis. And so in this case, you can, for example, compute given any current size. So here on the A, we're giving a constant current, and we're producing a constant spiking rate. And that constant spiking rate we can calculate on the basis of the solvable analytical equations we had before. And we can then produce the plot in B, where the non-dashed line, the continuous line, is what would happen if you continue to increase the current indefinitely in this neuron. And you see that it rises linearly because the frequency of firing is going to be proportional to the total integrated current, and indefinitely until, you know, hundreds of thousands of hertz. But that doesn't make sense, because in reality, we know that the neurons, even the fastest firing neurons, they have a cap at about, you know, like if they're going really super, they're going at 1,000 hertz. And the way that people then bound the leaky integrated firing neurons not to produce these indefinite frequency rises is by adding not only manually a resetting state after the threshold, but also a little period of refractoriness. And so you can think of this, think of it like this. Here is the QuickTime player. Can't, Juicy? I mean, my wife is calling me downstairs, so I will check on that in a moment. I apologize. I have a 3-year-old at home. Just quickly. So if we then have a ongoing current injection that is producing an ongoing current deflection, and that we're cropping at a certain threshold and resetting it to a state, we add a refractory period here manually. Say, okay, so during this time, we're not integrating. We have computers, we can say that, when, you know, for the next 5 milliseconds, do nothing. And we start integration again from there, put another refractory period, start integration from there. The spikes are virtually added on or where the threshold is. And this is then the resetting level. Here, this is V, and obviously the yellow is I. So if you have this kind of dynamics, then your rise of frequency as a function of current is no longer unbounded, and it becomes this dashed line here when you add a I think, what do you see? An absolute refractory period of 4 milliseconds. So if you add 4 milliseconds, then the maximum frequency that this neuron can have is about 200 hertz or 0.2 kilohertz, right? So this is then the dynamics of the leaky integrate and fire neurons. And there's a bunch of things that they cannot do. So they don't have any threshold adaptation. They don't have any adaptive spiking. You know, if you keep a constant current as an input, they're going to be producing the spikes at a constant rate. They have no resonance spiking. Like, you know, if you do 2 stimulus at a certain time, they're not going to respond differently. They're always going to respond the same way. They don't burst spike. They don't produce subthreshold oscillations. They have no hyperpolarization induced spikes. So if you increase the hyperpolarization, they're not going to spike. So all of these things the ADEX can do, but the IF cannot do. However, the one thing that it can do, and the reason why it is so heavily studied, or it used to be, especially in, you know, some the onset, maybe 20 years ago to 10 years ago, this until the 2010s, people had a huge amount of research going into this because of first, the simplicity, as we mentioned before, but second, the fact that it's a linear encoder gives a lot of lovely analytical and computational properties, and with the benefit that they actually emulate the pyramidal cells of the cortex. So here is a surprising fact. Christoph Koch has made a comparison between the spiking times and frequency of a Leaky integrated fire compared to a highly detailed physiological model of the Hodgkin-Huxley, of the pyramidal cell of the human cortex. I think it was maybe a mouse cortex cell, but in any case, a layer 5 pyramidal neuron. Don't know if it's mouse or man. There are differences, but here, the main fact remains that the faint line of the integrated fire closely tracks the highly detailed compartmental model for those parameter domains for which you have linear integration capabilities. And so those parameter domains in which you have linear integration capabilities for the non-spiking neurons, such as the pyramidal cells, they resemble closely that what you have seen in your own projects here. So we have so some of you that might have had machine learning, when you were computing the current against frequency plot for all of the 3 different kinds of neurons as we had before, you might have noticed that the firing rate relationship with current, it looks very much like a rectified linear unit, so a ReLU of the modern artificial intelligence developments. So it actually responds fairly linearly. It doesn't say anything at all up until a threshold. When the threshold is reached, it starts producing spikes at a low rate, but that rate increases linearly with current, which makes it a very good encoder of information, especially if this information is coming from an already sort of linear range. And for a vast variety of sensory systems, the majority of what happens is in the linear domain. And linear domain basically means you're looking at a picture and there's no color distortions in it. You're looking at the page with a printed photograph. The reason why, in general, you can see the picture is because there are no non-linear interactions between the colors. There are some, and illusions are based on them. But the core of the encoding capacity is given on the linear domain, also for our sensory systems. When it goes nonlinear, we have illusions. But when we're in the linear domain, we have a faithful reproduction of what our sensory system is receiving from a physical world out there that has a structure. So this is what I wanted to give you as an introduction of the Leaky integrated firing neuron. It has a lot of no's. There's a lot of things it cannot do, but it is powerful and it's representative of a vast class of neurons. And the project that we're going to be dealing with today is going to deal with Leaky integrated fires, imagining a cortical-like context where some of our conclusions might be relevant. And particularly, some cortical dynamics, as we observe, up and down states, they're going to appear in the project, or cascading dynamics, they can be explained by the somewhat simplified but rather powerful Leaky integrated firing neuron. What time is it? So it's 9:55. I didn't tell you all about dynamics. I'm going to transmit that for the next block of our lecture. So my suggestion is now I go and check what my wife wanted when she called me a moment ago. And at 10:10, we reconvene. I will then tell you more about spiking models, synaptic models, about models of connectivity, and about random input, imagining what random input would be via Poisson processes. Okay? So questions should come now, if they are there. So I have to get my chat back here. So you have questions? See? Questions, comments, doubts? It's simple enough, I guess, but I still think that there is space for a lot of confusion. A lot of confusion. I hope not. There's space for some confusion. Well, it might address them posteriori when we return. Think about questions, and at 10:10 we return. Now, okay, we are going back to our requirements to build networks of integrating fire neurons, and we need to discuss a little bit about synapses. So there's many ways to conceptualize the synapse. You know that as neurobiologists, you definitely know that it's turtles all the way down. The complexity of the general synapse is just momentous. We can conceptualize it more or less as for the majority of ligand-gated synapses, and I'm going to get to all types of synapses in a moment. But in general, an action potential is produced in the presynaptic cell and the soma, or initial segment of the axon, because of the high concentration of sodium channels. Then it propagates down the axon. When it arrives at the presynaptic terminals, so here we have the presynaptic terminals on top, it fuses with neurotransmitters such as glutamate or GABA with the membrane via complex calcium-related cascades and reuptake and all sorts of complexities. But you know, action potential descends to the axon. Voltage change at the level of this.
Connect niet met.
There's someone has, yeah. So at the level of the presynapse, fuses vesicles, releases neurotransmitter. The neurotransmitter diffuses along the cleft, is taken up by the postsynaptic receptors, which induce either conformations of the receptors themselves, ion channel type, like conformations of these ion channels, the synaptic ion channels. Effectively, receptors are synaptic ion channels, or secondary cascades inside the cell that also induce conformations of ion channels related to that particular protein. And that creates conductance changes at the level of the membrane. Conductance changes relate via the driving force to a current, and that current comes in and percolates then through the dendrites towards the soma of the postsynaptic cell. You know, at the level of generalities, we can speak about synapses in that case. All the biological complexity has a few categories, and these categories fundamentally different activation mechanisms. They're very interesting and relative and important. So broadly speaking, we would have the ionotropic synapses that let ions pass directly after binding with the neurotransmitter itself. Those are examples of the most common excitatory and inhibitory transmitters modeled. Some of these first being found. So AMPA, NMDA, and GABA. So in the case of AMPA, you bind directly with glutamate. In NMDA, you need both the glutamate and magnesium to bind. And in GABA-A, you need GABA is an inhibitory neurotransmitter. AMPA and NMDA excitatory, GABA inhibitory, but all of these ionotropic. Then you have metabotropic receptors. I guess that you already know this, but these are the ones that let ions pass after the take-up of the neurotransmitter and secondary cascades in the synaptic site. And these would be the neuromodulator neurotransmitters, very many of them associated with a grand many alterations of psychological functions, such as serotonin, creates some sense of inner peace and tranquility, dopamine, you know, like excitement and reward, endocannabinoids, the munchies, and then you have electrotonic synapses that are simply connections cell to cell. They don't have a cleft. These synapses, they're basically proteins that exist across the two synapses, and they make one cell talk to the other. These are the gap junctions. You might have heard about them before. So no transmitter is related, and the amount of current coming through is a direct function of the difference of potential between the presynaptic cell and the postsynaptic cell. I'll have an equation. But ultimately, what's happening is something along these lines. You have so in panel A, you have a traveling pulse that arrives at channel B. If you measure the voltage at the postsynaptic soma, you notice that the event induces a rise of current and then a fall again. So the rise is the current being integrated, and the fall is the voltage leaking through the membrane. If you get if you get signals from the presynaptic cell in quick succession, they will add up and they will mount on each other. In this case here, we see the mounting, and they haven't reached a threshold, but this is the notion related to integrating fire neurons. And if you have now, say, two cells sending a bunch of spikes, we can see that they would add over time, and particularly if they come closely related to each other. These synapses being depicted in this picture are conductance-based synapses. We're going to get to them in a moment, but the conductance-based synapse has the particularity that the closer they are to threshold, the higher the gain of the integration of the synaptic current. So you see here that in the first pulse, the integration is small. That's because we don't have any voltage-related gating via sodium, for example. And when at the fourth signal that the cell is receiving, it's already becoming fairly steep, and that's because it's already close to threshold. So we have a high dependence of voltage on the current because of, say, open M channels. And so this summatory, nonlinear summatory effect, these would be conductance-like synapses, but they are valid in if you're thinking about other kinds of synapses that are more linear as well. In Hodgkin-Huxley language, a conductance-based synapse would look like the sum of the receptor conductances, so basically how many receptors are there in the membrane, all of them, and times their own individual conductance, so like per receptor, per protein, times the proportion of open channels. So here I called it eta in this little function, and times the driving force, the height of the fall. You notice that the V synaptic or you know, the equilibrium potential of that particular synapse, because the synapse is permeable to certain ions, and so the difference of potential, or the equilibrium, the resting, the equilibrium potential for that particular synapse would be related to the channel, to the ions that it's permeable to, right? So in the diffusive electronic concentration balance. And here's a comparison between different kinds of conductance-based synapses in terms of the current that they let in the cell. And you can see, importantly, the immense difference that there is in their constants of integration. So AMPA is a very, very fast process, right? So within the 5 to 10 milliseconds after the arrival of the presynaptic current, you have a sharp rise and a sharp fall as well. So glutamate binds, fast current, down. GABA A is also a fast inhibitory transmitter. So it creates a negative deflection in the current. I mean, it basically hyperpolarizes the cell, it inhibits the cell. And it's a little bit slower than AMPA. GABA B, however, is very slow. So this, it binds, it's a metabotropic receptor with a long secondary cascade. And so after the neurotransmitter being taken up in the synapse, it takes a long time until activating those receptors and an even longer time to come back to baseline. So this is highly associated with homeostatic function in synapses. And then MDA, which is related to long-term plasticity and learning in the hippocampus, particularly via binding both of glutamate and magnesium. Not super relevant, but since you have heard about these ions before, it's important to at least know that NMDA then will be longer active excitatory channel and is related to the expression of new AMPA channels. Basically, when you activate NMDA channels, you depolarize the cell to a level where it is more keen to express new receptors, thereby inducing plasticity. We're going to be talking about plasticity on our final lecture, like in detail, about unsupervised plasticity and plasticity mechanisms. But for the moment, these would be four of the most prevalent synaptic currents and the synapses that you would like to learn about. So here we have a little model portfolio for the synaptic types. And you can, for example, so I'm going to go, so you can have simply a current input. Say you're programming a neural network, and in your neural network, you imagine that the easiest way to go about it is just to, every time that you get a presynaptic event, like presynaptic cell produces a spike, you just simply add a bit of current to your cell. No matter what voltage your postsynaptic cell has, you just add a bit of current. It's a very simple way to go about it. It's probably good, actually, in the case of exclusively excitatory currents that are fast, and so you can just add a little bump of current. However, it does not take into account any kind of conductance modifications as a function of voltage, and so it's a constant current, right? So the current base is a constant current that enters the cell after an event. Then you have the conductance base, and I'm going to go quickly over these in a moment, which can be some sharp rising functions. An alpha function, it's one parameter, smooth rise and fall, can be modeled by a double exponential. So if you're fitting these functions, now think back to computational science, these are the currents you measured in experiment and you want to model them via curve fitting. So these, basically the first three, are choices of which curve you want to fit on. And then the fourth, which is a Markov channel, is a more plausible way to look into the different conformations that the ion channels can take, or the receptors can take, as a function of their uptakes. And then finally, we have the gap junctions. Let me quickly walk you through what the conductance-based would look like. So this is the portfolio, and then now you can see on the left side the equations, and on the right side, focus on the right side of what's going on. So you get a pre-spike, which is an event. There's release. We don't talk about quantity of neurotransmitter being released. It's just basically a release, and we imagine it's quantized. It's always the same. And the excitatory postsynaptic current is a function of the conductance of the synapse that we've received, times the bar of the synapse, and falls slowly with the deactivation. So this is exclusively of the receptor dynamics itself, right? So this is not the cell. And then you have the excitatory postsynaptic potential, so P and C, current and potential. Potential is what kind of current rise that sharp event leads to. Compare that with the alpha synapse, which is a one-parameter family function with a single tau, determining both how sharp it is and how both the sharpness of the rise and the sharpness of the fall, or the smoothness of both. So only one parameter regulates. Basically, it's not infinitely fast like the alpha function. It is has a certain rise time and a rise fall, which leads to an excitatory postsynaptic potential being a bit smoother. And you can also have like a mixture of exponentials in which you would separate the rise of the synaptic current from the fall of the synaptic current, thereby trying to be very appropriate about the current influxes in the cell. This is a Markov channel, however. I don't know if you've already encountered Markov channels in, and so not a receptor, but a channel. Like I'm going to present you the sodium channel, but this is the same for the, there are models for AMPA and for GABA that are based on this formalism. I just think that this is nice to introduce. So just bear in mind. Here, let's first focus on the big letters. We have states, C3, C2, C1, O, I3, I2, I1, I. Can you figure out what these C, O, and I stand for? So this is the sodium channel, the common sodium channel that I've introduced also in Hodgkin-Huxley project. And these are and connecting them are particular transitions. They have a forward rate or a backwards rate. So the letters represent the states that the sodium channels can have in this case. There's three ways that it can be closed, three ways that can be inactivated. One way it can be completely inactivated, all closed and inactivated, and one way in which it can be open. So this has to do with how these subunits have conformations. When we are talking about a C3 state, is that the three sodium subunits, or the three subunits, are all in their closed conformation. Then there is a forward rate that would transform these three closed conformation subunits into two closed conformation subunits. And there are three ways you can do that, right? So you can either open this one, or open this one. That's why then you have the 3 alpha M connecting the C3 to C2. This would be the forward rate. So the rate that channels change from C3 to C2. Remember, this would also be a function of voltage. Would have to measure it experimentally. And B is the reverse rate, the way in which they have to change it. There's in any case, when you have one of them only open, there's only one way to close, and that's why your beta doesn't have any coefficient. There's one that's coefficient, only one way. So this is a probabilistic way to look into what are the possible transitions between the different conformational states. So on the bottom left, you have state I to state J has a forward rate Rij and a backward rate Rji. And then you can transform from this graph, you can derive a master equation that will give you once you have the rate, will give you the change of state and of the individual potential states that channel can occupy. So the master equation, dSi over dt, returns to every possible state. So a Markov channel, instead of only having, say, in Hodgkin-Huxley, m does it all, right? Or actually M and H do it all, right? So you have two variables, two state variables only. In a Markov model, you would have here 8 state variables, right? And they would represent the proportion of channels that are in each of these conformations. So if you have 1 million of channels and all of them are closed, then your C3 state variable will be 1 and everybody else will be 0. And with the forward and backward rates, we can then measure them. So this is a Markov model of a channel for you, and it's also a Markov receptor. There are many ways to look into these forward and backward rates by selecting, by doing crystallography and understanding what the relationship between the voltage and currents are, and also by doing single channel patch clamp. I wanted to show you here that even though there can be different models of the same ion channels, in this case it's also sodium. These are for A, B, and C, you have 3 different Markov type channel models, and they are substantially similar, even though they have a lot of different number of states. No, so this is like, so sometimes complexifying the model, which is the correct model, is the question that you would like to ask yourself here. Might not be entirely obvious. If you're actually computing a large-scale model and you want to use Markov models, then probably your best choice is C, because you only have 3 more state variables to handle. If you're going to take the elective on high-performance computing from Christos, he will tell you for sure, just take C, because you have much less memory you need and many fewer differential equations you need to compute. And on D, you see a comparison between these different detailed and simple models within a Hodgkin-Huxley model. Now, before you go saying, oh my God, Hodgkin-Huxley is totally wrong, it's broken. So we're looking into a very fast process here. We're talking about 0.1 milliseconds. That's 1/10 of the duration of the overall Hodgkin spike would actually take more than 2-3 milliseconds. So this is at the onset of the current injection. And what you see is that the detailed model has somewhat of a faster rise. In fact, it opens more channels. The simple model has a bumpier transition to open, and that makes sense because there's from close it can go in immediately to open, whereas for the more complex models you can have multiple combinations of closed. So but this is strictly at the very onset. Then you will say, oh my God, I need to use Markov models because look at how much more detail they have in them. Remember, we're tuning these behaviors via parameters. And so if you actually tune your Hodgkin-Huxley M well, you might actually be able to obtain very similar curve shapes. So ultimately, it's about the curve shape that you are going to obtain as a function of voltage. You can induce more detail, but the level of accuracy might actually be identical to a simpler model. One of the recurring themes of this course, but I wanted to make the point as well that the same is true for synaptic models. These are the kinetic schemes for AMPA and NMDA. You see they look the same, and that's why I presented the sodium first to create the relationship between receptors and ion channels. Receptors are activated via neurotransmitters. The ion channels are activated via sometimes ligands, calcium, or simply the difference of potential. Oh, and there's one synapse that I wanted to tell you about because it's an important synapse, and there's a slide missing here. So I'm going to bring you quickly to the QuickTime player, where I have my iPad. So if you have cell 1 connected with cell 2 via a gap junction, this is how you symbolize it. It has basically a resistance between the two, and it's not the amount of current going from 1 to 2 and or 2 to 1 is a function of the difference of potential between V1 and V2 via times the resistance. So since the resistance is constant, resistance, conductance, potato, potato, G, the amount of current coming into cell 1 is going to be the difference between the potential of cell 2. So if cell 2 is more depolarized, cell 1 is going to get current. So it's going to be V2 minus V1. And this is the coupling current between cell 1 and 2 via gap junctions. Fun, trivial. Gap junctions are super important. And if you connect many cells that have resonant properties, the fact that they are trying to equalize themselves is also very homeostatic in nature. So if you have multiple cells and all of them are connected via gap junctions, they effectively can act as a meta cell or a mega cell. And insects use this trick quite a bit. But if you then get input into one of them, they can spread as waves. And this is also a common behavior observed in many areas of the brain, including the one that I study most keenly. So just wanted to tell you a little bit about this other type of synapse before we move into Poisson processes. This is another component of networks. Okay, so finish. In this component of networks, I prefaced the lecture today by talking about, studying random networks, the gain in knowledge that we have via studying networks in their most pristine scenarios. Like when we make very few assumptions. What if it were all random? They're connected, they have synapses, but what if it were all random? Let us look into the assumption. Maybe the brain looks random. And a lot of people, in first recordings, they were like, wow, this makes no sense. We've transitioned a little bit from there, but people were observing spikes and trying to figure out what was the baseline firing rate of the neurons, and they saw that the variability looked very impressive. I mean, they give a steady current, and even in a steady current, you would see variability, as I showed you when I was talking about reliability of Hodgkin-Huxley models. A Poisson process is a way to imitate very random neurons. It's a statistical way to imitate very random neurons. Can I ask you a question here to interact with me in the chat? Today's been like fairly one-directional, so I would like you to tell me if you have already or have never heard about Poisson processes. I think in nanobiology you might have heard a lot, and so I just will gauge how much I want to talk about it as a function of how much you already know. So would you kindly just, say a 1 or a 0? 1 means I have heard about Poisson processes. 0, I have never heard about Poisson processes. Wow, that's overwhelming. That was so nice. Okay, NB3014. Okay. So flyby. Flyby is good enough for you guys, right? So flyby in the context of neurons. This is a recipe to create a Poisson process. You determine the rate of your random events. That's the probability of an event. You take an interval to spread them on, say 1 second, and you say like 50 hertz. You break the interval in small pieces, such as only one event can fit in a bin, say a millisecond. And then for every interval, you produce a random number between uniformly drawn from 0 to 1. And if the random number is smaller than the probability, we create an event, or effectively we spike. The nice thing about the Poisson distribution, like I'm not going to belabor this slide, the idea here is that you see different curves of probability of seeing certain spikes as a function of the rate R, normalized by the interval. Poisson is very close to produces very close processes to randomicity, and so you see the Gaussian on the right side that is generated via Poisson. distribution. It's not identical. It's not a Gaussian process, a Poissonian process. Now, I mentioned a moment ago that people, when they started looking into brains, they were measuring things like the interspike interval between between spikes to try to find out what was the distribution of interspike intervals. So if you have spikes over time, 1 millisecond, 7 milliseconds, 20 milliseconds, you can look into what's the waiting time between any two given spikes and plot the distribution of the frequencies of these waiting times, the interspike interval histogram. And here you see the comparison between a Poisson process on B and an actual distribution from an MT neuron. MT is mediotemporal cortex neuron. It's related to motion perception. But this is spontaneously produced by the cell itself. And it would seem that in this spontaneous case, it is pretty well matched by the Poisson. Obviously, would do a lot of statistics here to validate this, and they've probably done it, even if the original publication 1994, they already had statistical tests back then, and they tested these Poissonian assumptions. This is most likely then, you know, is an example of a vast number of publications that were looking into neurons and discovering that for all intents and purposes, they would even look random. All right. Now our understanding of this relationship between random distributions and actual brain function is more sophisticated, but and we understand them better as a function of the networks they're in, but there's still good representational models of what is coming from an incognizant neuron. So say you have some neuron in the brain and you're looking into their synapses, how would you model the incoming events? I mean, one way is to create all of the neurons that are projecting to your neuron. And for one neuron, you have 10,000 or 100,000 or 500,000 neurons projecting to a single neuron sometimes. And so you would have to create 500,000 models. And what do they get? So instead of going there, there's a much easier way to go about this, which is to just create Poisson processes and see what happens as you change the rate, right? And the rate represents all the possible random combinations. Okay, so this slide talks about the variability that you observe when you inject a single when you inject current in a current injection in an in vitro neuron that have been removed. So you see it's fairly irregular. But if you inject the same current in a neuron that is inside the brain, you see a lot of this stochasticity. So that's another motivation for the Poissonian variability. I mean, if you take the neuron in the context of the other neurons, it has a fairly Poissonian distribution. This goes back to the slide I already showed you before. So if with constant currents, we get fairly variable statistics, but if you give it a repeatable, say, Poissonian input to this neuron, it would also be fairly reliable. So this is then recanting back from it's random to its precise duality. It would seem, as most neurons, they are, given what they are, they're precise, but the population of neurons is so vast and so different that it's really hard for them to use that precision in profound ways. So we're not, I'd say, we're not a quantum computer at all. But let me not get distracted. Okay. So this is so much about Poisson processes in the brain. Poisson processes are good models for events when you're having an input from a different area. What time is it? 10:47. So it's a bit faster than I had expected, but I think it's nevertheless okay. It will give us about an hour, 10 minutes for us to play with the project until we reconvene here for some questions. And for that discussion, I would actually like you to share your video and to maybe prepare a couple of questions during the time you're gonna do the project. I'm going to share now with you the Google link. As previously, most of this has already the solutions for the exercises we're proposing. Some of the questions do not have specific answers, and I would like you to very carefully think about them. We are still using Brian for the simulation of SpikingNetworks. And towards the end, what we will be interested in doing is looking at a network that has both excitatory and inhibitory synapses and learning about what are their dynamics, what parameter domains they have, particularly during this kind of spontaneously or Poisson-driven input. Also, give some examples with more structured input so that you would know how to drive Brian, for example, with other functions such as sine wave. Doesn't have to be always Poissons, of course. And then we're going to be looking into the emergence of synchronization in these networks. I'll fire up Discord. The link is already there. If you have questions about synaptic currents or about synaptic currents or about Poisson noise, shoot them in the chat. I'll answer over there. And I'll also put now in the chat the project. I'll also add the project to, I think that this right? So I hope that this will take you there. Give me the thumbs up if it works. And then I'll meet you in Discord, and I'll also put this in our in content for lecture 3. It works perfect. So lovely. So it doesn't work in Brightspace. I guess that's because I should say that it should open as an external resource. Okay, I'm going to be figuring this out offline. And yeah, if you have questions and if you have comments, I'm keen to look into them in Zoom. And we will be transitioning now to Discord. So see you soon, and get ready for the discussion at 12. Now, let us begin with, is the screen being shared? Our secret TA channel. I want to mention a couple of things about our choice of Google Colab to do this code. So as you may already know, this is IPython that you're using Jupyter notebooks, basically. And there is stack dependence on which code has been run previously on whether the code that you're running now is going to work or not. And one of the things you have to do quite often is restart the runtime and run all of them, all of them again. And that just to sanity check that everything runs, it's one of the easiest things to do. Another thing to note is that you can have also the you can display the executed code history, so that you keep track of which cells have been run already. So if I run cell 1 and then do the pip install Brian line, it will record here in the executed code history. So you can more or less keep control of this. If you're using Python developing environments, you can also have a workspace like in MATLAB and look at the content of your variables and so forth and so on, although you cannot quite do it here. Can also have diffs and make comparison between different states. So these are some nice features of Colab I wanted to point to. There's one more, which is here. If you're connected to a runtime, you're basically connected to a Google server that is running this for you. So this is the first option, connected to hosted runtime. But if you are offline and you have a Jupyter installed, you can also have a local runtime and you have your own computer serving the IPython notebooks. So you would have to create a local Jupyter install, and you have to make sure that Google Colab can see it, but then you can also use Google Colab with a local install. That's very convenient. With the notebooks, there are other facilities than you can have if they're local. But this is so much about Google Colab itself. I would like to know from you, so now we have 16 participants. The amount of folk dropped on half, so I guess that many of you have selected to do the project later, which gives us the ability to discuss kind of in a big panel forum like. And if you would like to, I would also like to take your questions in audio and jump in, just basically come up and shoot a question or in the chat. So feel free now to ask questions about the project or about Google Colab or about the projects in the end. So the presentation slash reports. I know that there were some questions as well. So feel free to use this moment now to shoot your question about any of these topics. I'll be here waiting for you to jump in and start talking. So unmuting your phone. My loudspeaker is ready, and I suppose that everything is working. So feel free to do so. I have to stop my runtime. And while I wait for your questions, I am going to. Oh, okay. I tried asking this in Discord, but can you maybe tell a bit more about the big project, the potential projects on Brightspace? Research and demo, research and discuss, implement and demo. But what does that entail? Emma, can you come online? Can you ask this via microphone? Because then we also have recorded the answer.
Hi. Yes. Well, maybe there are some problems with Wi-Fi, but you will notice. I saw the potential projects, and sometimes it says research and discuss. Sometimes implement and discuss, or in demo, but I'm just not sure what it means.
Interesting.
I mean, the research and
So it's
implements
to find out
that's
about a
fine.
topic,
But
right? So basically the research and demo is the idea here. So first off, the projects are very open in scope. What we're trying to do is to continue the process of priming you into neural networks and explore parts of this that we have touched or have not touched yet. Demo often means to just demonstrate a piece of code. So for example, I'll show you here what I mean by demo with neural networks in behavior. In fact, the project we have right now has a balanced excitation inhibition component, and you could demo that basically. Oh, this is what happens when you change that variable. So demo really means, you know, you're giving a sense of interaction to the project, if that's clear. For instance, I don't know, I could demo a piece of code that gives us, so something like this. So I have here another different programming environment. It's called Mango, and it is often used to also have integrate and fire neural networks. So if I press play here, I see spiking rates of a group of 100 neurons, and I can change the stimulus here. Now, no one is understanding anything of what I'm doing because I'm not really properly demoing it. I'm just showing the idea behind demoing. The idea behind demoing is to present an on-the-fly piece of code that does something interesting to others, and so to explore what has already been coded potentially. So demo means you don't necessarily have to code yourself. You can simply demo. You go there, you pick up code from someone in GitHub or some other place, and you demonstrate to the others how it works like. So research means, you know, what are the interesting questions behind this particular approach. Is this clear? Does this make sense?
yes, I think so. But it makes sense with if you made a code, but if you only do research, do you have
Yeah, I mean, if you
something to
only do
demo
research,
then?
then you have no demo. That's why I kind of like
Yeah,
put the
okay.
word demo there. So because it would be nice to have something, you know, extra, something that something more
Okay.
practical, in
Yeah,
essence,
I get
to
it.
introduce some people to some resource that you may or may not have found. I can also help you finding resources on these things if you ask me questions about specific choices.
Yeah. Okay. Thank you.
Yeah. Okay. Any more questions on the project? So the time that we will have, I think that it's important. I say now, since we're discussing this, I'm going to put now a Google Sheets page for you to self-assign what topic you want. I don't mind if topics overlap, so it's okay if two people have the same topic. That also actually gives more room for complementing each other and looking at slightly different angles. I think that individuality usually allows us to do this. Also, the fact that people focus on their preferences also gives focus to the projects in the end. The overarching topics then would be something like neural dynamics. Okay, so then Google Sheets where you will self-assign which project you want if you're working with one or two people, and just so that everybody has an overview of what everybody else is selecting. I will put that in Brightspace as a notification as soon as we finish the session today. Let me see if something else. Yes, and then the time allotted for the presentation will be decided on the basis of the number of presentations that are taken up. Right now, and the overall time available for our last encounter, which was the exam day. And I think that we have the exam day 3 hours, and we're going to do this pitch style. So it's going to be fairly short presentations with a couple of minutes for questions. The idea is to divide simply the number, the amount of time by the number of people. And if you're presenting with 2 people, you're going to have as much time as so the time is allotted per person. And so if you have a group with 2 people and the time per person is 5 minutes, the 2 people get 10 minutes. And so if there's 1 minute for questions, then 2 people per person, 2 people have 2 minutes, right? So we're going to have exact ideas of the dimensions once everybody put their names in. But you can already have an estimate. If we have about 40 people total in the class and most people take groups, then we have 20 groups and we divide 180 minutes by 20 and 90 minus some pauses, maybe 15 to 20 minutes in a group for 2, hopefully. I didn't do a precise calculation, but 20 minutes per group would seem reasonable. Let me see if there are questions in the chat. If you do have other questions. Okay, so Niels, can you come online and ask your question, because then it's recorded for the people listening afterwards?
Can you hear me?
Yes.
Okay, so what Emma just asked, the demo would then be the presentation, and you would be actually graded on this demo as you have to write a report about the demo, or you can have the option of coding yourself and then explaining the presentation what you have coded.
That's right. So if you coded yourself, the commented code serves as a report. If you have used someone else's code, it's nice to write a report about it so that you demonstrate that you've got in touch with what the code is doing. So it's fairly high level in terms of functionality. So the report one possible report would look like little intro about the general problem, introduction to what the method is, the topic, the actual software you're demoing, for instance, and then a couple of screenshots and relevant code blurbs, or even some extra information that you feel relevant. So it's fairly open in scope, and the idea is to really enable anyone to discover what they want in the ways that they want. I was thinking potentially to also share the presentation slides from last year. We have now 15 people online. Can you vote on that? Because I think that on the one hand, it's nice to see what other people done. On the other, it has the problem that it will constrain your thinking. And so,
yes,
tell me
and
what
maybe
your preference is. And,
maybe another question I wanted to ask. Because you say that these projects they're very different topics. So you have one that is about which direction should Pac-Man go, or if a cricket flying in the wind.
Yeah.
How do we, if you, for instance, wanted to implement such a thing, or in this case, write a demo, should you have like use the material you discussed, or can you also go out on a limb and have?
You can go out on a limb for sure.
Like machine
it's not
learning
much time,
style.
so it's basically to show that you've done some exploration of an extra topic. Next week, I'm going to talk a little bit about population encoding, and that's when we're starting talking about tuning curves and so forth. And so some of these topics have not been introduced yet naturally, and so you can then decide which angle you're going to complement it on. I'm not going to be demoing myself these things that I'm asking you to demo. I'm just going to be talking about them. So I'm going to say, oh, the cricket hair on their legs receives wind from different directions, and we know that there are receptive fields in the individual hair cells, and we can reconstitute or decode the direction of wind as a function of the wind direction, as a function of the activity of the sensory neurons. And then you would go ahead, oh, I implemented a network that just does just that what you've described. Make sense?
Yes, that makes sense.
So the demo is then the presentation you will be graded on, and you write a report about this demo. Yes, and then 50-50 presentation and demo. But don't overthink it. It should be clean and clean and topical, concise, and not introduce too many things. I mean, try to constrain to one aspect of the topic and hammer that one. I'm going to put the presentations online since Emma jumped in and she said it would be nice to have inspiration. I guess if you don't want inspiration, you don't need to look into the previous slides or copy them. Anything else? Okie dokie. So is the date for presentation already known? It says 3 hours on the 28th of May. That's when the test is, isn't it? I would have to confirm. So 3 hours, 20 groups, so 180 minutes. So that's 9 minutes per person, 18 minutes if it's 20 groups. We will release the exact numbers later, but it might be 15 or 10. So 2-3 minutes should be okay to flexibilize. That's why I also said it has to be topical and on the point. Ever see? Tentamen. Yeah. So in my calendar, it says that the test is on the 29th from 9 to 12. 29th, yes, 29th. So there's a lecture on the 28th, and on the 29th we have the presentation. It's a short course. It's very compressed. So if we want presentations, this is the way we can deploy them. I did debate an online test or things like that, but I think in the spirit of this elective presentation is a better representation of what has been learned. When I say demo, by the way, it's safe to presume that there are demos out there in the internet that you can find that do certain things and then represent these ideas. Also videos, like it's okay. It doesn't have to necessarily be interactive, but just showcase something, showcase an approach. So showcase a way to complement the neural network knowledge in the spirit of the primer. Should really write that these projects are non-exclusive. Keep the questions coming and I'll answer them. I will introduce you, by the way, to this next week, so you don't have to be dangling in curiosity. It's a cliffhanger. This is very cool, a simulator as well. I'm going to stop sharing my screen because I'm going to be doing some stuff here in the background, okay? But I'm still available for questions about the project, and I would actually really like to have them if there's anything that pops up for the next 10 minutes or so. Okay, so we do have a question here from Daphne Cornelissa, and the question is, can you talk a little bit about the analog plot in the project? I can, and I will, and I can even present you with a couple of other examples. So let me share my desktop once again and go back to the plot that she means. So we started this project by talking about the rasters, raster plots of spikes. Right? So a way to look into when did the neuron need spikes, and it's a way to quickly grasp what's the firing rate of the neuron. But it doesn't tell us anything about what's happening under the cover, right? Because spikes are only what happened above the threshold. And so we basically are lifting the, we're lifting the blanket from under the spikes and looking into other variables that are contributing to spiking in a more continuous way, so in an analog way. It's fundamental to see that in many cases, particularly when you have more sophisticated networks or where the dynamics of the individual neurons are not as trivial as the integrated fire. Nevertheless, as a tool, it also gives us other angles to look upon the activity of the network itself. I think that I've actually said something about the tips of the icebergs. Here, for example, you can also spot, since you have a color, when the neurons synchronize, it's easy to see that by spotting what are the groups of also the ones that are not spiking but are somewhat synchronizing. You would then see them as bands. I'll give a specific example of this from my own research in the inferior olive. So here, inferior olive is a part of the cerebellum that produces the complex spikes in the Purkinje cells. And I will show you from a recent talk I gave on Monday morning. I think I have a nice raster out there. Maybe I do, maybe I don't. Not in this one. Less recent. So let me see if I have a good example. So this is, for example, an analog raster with a probability density function of spikes on top. I suppose you can see my screen still. And there's a lot of details in this plot that you don't necessarily need to understand, and I'm not going to go through all of them. But one thing you see here is that some cells have subthreshold potential. So in this case, I actually also overlay the spikes themselves that the cells may produce here in green. And one thing you see here on the left side of the screen, you see the neuron. So neuron 0 had produced a little spike at this moment. And when it produced a spike, it just so happened that other neurons had already had their membrane potentials more or less aligned. So here we're plotting the analog membrane potential, and these cells are spiking. If you kept only the spiking raster, the only thing you would see are the green dots. But because you have the membrane potential, you can see that even the non-spiking cells here, they also synchronize. And in this case, they synchronize because they're connected by gap junctions, the synapse we talked about earlier. And you can see here that all of these cells, they had a little bit of a depolarization event. So they synchronized their membrane potentials and they synchronized their hyperpolarization. But they did not quite synchronize spiking. And in fact, the spikes from the cells that actually produce spikes are not even that well synchronized. So the underlying membrane potential is more synchronous than the spikes overlaying. And that's one of the reasons why I presented this to you, because I just wanted to give a little bit of a richer view of spiking, because not only spiking, what goes underneath is also important, right? And so this is why it's there. Daphne, is this nice? Is this clear? And so that's why the analog raster is there. So it gives you a peek under the hood. What I wrote over there is like the spikes are only the peaks of the iceberg. So you're basically seeing what's under the water. Yeah, peek under the hood of the networks. A nice way to debug networks as well. And you can sort them in many ways depending on patterns you stimulate with, and they become very visual. Not all projects benefit from them, but they're a rich visualization. You've probably seen multiple color plots like this in MATLAB and Python. That's a question. Okay, I will just say what we're going to see next week before I love you and leave you. So next week, we're going to start focusing on encoding per se and simplified neural networks. We are going to look into distributed representations of neurons. And so I'm probably going to start pretty much from this actual page here. So this very same neuron, which is a 100 neuron integrate and fire network that is encoding a two-dimensional stimulus. We're going to be talking about this next week. And with this, have a great week. Have a great internet connection and blue skies all over. Have a good time.